So a very, very warm welcome to all of you to Imperial College London. So my name is Washington Ochieng. I'm the current head of the Department of Civil and Environmental Engineering here at Imperial. And it's my pleasure to serve as chair for this evening's event and to welcome you all to this professorial inaugural lecture by our Professor Robert Vollum, who is our professor of structural concrete. I call him Robbie, and the reason I do that is because he hasn't actually told me not to do that. So I will continue using it if you don't mind. So whether you're here in person or joining us online, you're most welcome, and thank you very much for attending. I'm being ably assisted this evening by three members of Professor Vollum's research team, postdoctoral research associate Abubakar El-Wakil, and PhD students Zayu Wang and Karim El-Khoury. Karim will be managing the online participation this evening. Robbie is a very brave man indeed. You know why? Because he has agreed to a short Q&A following his lecture. The tradition normally is that we don't have those questions, but he's kindly agreed to do that. So we thank you for that, Robbie. So we are encouraging you, those who are participating online, to please type any questions in the chat, and we will draw on a selection of those later following the lecture. And this is the interesting bit. This is where I tell you a little bit about Professor Vollum. He was born in Oxford, but spent his early years in Southern Africa, mainly in Zambia. He first came to live in the UK at the age of 13 as a boarder at St. Edward's School in Oxford. He completed his bachelor's degree in engineering science at the University of Oxford, where he attended St. Edmund Hall. He then worked in industry as a structural engineer with Arup Associates, before coming to Imperial College to study for an MSc in structural steel design. Should I say the year? In 1986-87 academic year. Henceforth, he returned to industry, working at Over Arup and Partners. He then returned to Imperial in 1991 as a lecturer in reinforced concrete design. While in post, he studied for his PhD, which was on the design of reinforced concrete beam column joints. Robert was promoted to senior lecturer in 2003, reader in 2011, and chair professor in 2020. So during his time at Imperial, Robert has established himself as an international authority in the field of reinforced concrete design, where his research is much influenced by his time in industry. So he gets things done, building complex structures and so on. His research interests in reinforced concrete design are broad and closely aligned to the requirements of industry. Over the past decade, he has made significant contributions to the development of design rules for shear and reinforced detailing and the next generation of Eurocode 2. Recently, his research has focused on the development of enhanced numerical methods for modeling punching shear failure in flat slabs. Currently, together with Professor John Forth at the University of Leeds, he is leading a major EPSRC-funded investigation into restraint-induced cracking in reinforced concrete walls. I was just joking with Robbie earlier that when I looked at that picture for the first time, I thought he was cracking up. And then I realized that actually it's not about that, it's all in the cracks. So Robert is a chartered civil engineer and member of the Institution of Structural Engineers. He's a member of the BSCI Committee 525-2, which is responsible for technical standards relating to the design of concrete structures. He is also a member of the UK National Annex Committee for Eurocode 2. He is the UK's principal expert on task group 4 of working group 1 of CEN-TC 250 SC2. Okay, the interesting simple part, This particular group developed the design rules for shear, punching, torsion, and torsion in the next generation of Eurocode 2. Robbie represents the UK on Commission 2 of the Fédération Internationale du Béton. He also serves on the editorial boards of the magazine of Concrete Research and Structural Concrete. Robbie is a very valued colleague in our department. He was director of the MSc program in Advanced Structural Engineering between 2010 and 2014, deputy director of our Center for Doctoral Training in Sustainable Civil Engineering between 2014 and 2020, and he is currently the CDT, or the Center for Doctoral Training Director, from 2020. It is my absolute pleasure to ask Professor Robert Vollum to please step up and deliver your inaugural lecture. Robbie.
Many thanks, Washington, for your kind remarks. Welcome, everyone. It's great to see so many of you here tonight. I'm particularly honored to welcome Professor Aurelio Muttoni, who's come all the way from EPFL in Lausanne to give the vote of thanks. It also gives me great pleasure to welcome my family here, and also welcome to everyone online, including my mum. Hello, Mum. So many thanks to many people. Over the years, I've been fortunate to work with many wonderful colleagues, too many to name, but 4 people stand out for me. Without their help and guidance, I wouldn't be standing here tonight. So first of all, I'd like to pay tribute to the late Professor Paul Regan. It was Paul who inspired me to investigate shear transfer through cracks. Over the years, I had many fascinating conversations with Paul about punching shear, as Monica will testify. The scope of Paul's experimental work into shear was sort of truly legendary. Aurelio and I were just talking about it now. He carried out experimental research many years ago that is still very pertinent today. I was also fortunate to work with the late Professor Andrew Beebe. We had many fascinating conversations about the influence of construction loading on long-term slab deflection. Andrew always brought a unique perspective to whatever problem he examined, and he was the master of the development of clear and concise design guidance. Over the past decade, I've been very fortunate to work with Professor Aurelio Muttoni on the development of the new design rules for shear in the next generation of Eurocode 2. Aurelio has been a great inspiration to me, and he's really convinced me of the merits of mechanically based design models, and I hope that over the course of this evening, I will persuade you as well. Last but not least, I'd like to pay tribute to my colleague, Professor Bassam Izzadin, who's provided me with help and support over many years. My special thanks go to all the technicians in the Structures Laboratory, with special thanks to Les Clark, the laboratory manager, and also Bob Hewitt, who you see on the right, fixing some formwork, not forgetting Andy Pullen, the brains behind the laboratory. My enduring gratitude goes to all my PhD students. Guys, I couldn't have done it without you. And last but not least, my family, particularly my darling wife, Claire, who has put up with me working endless weekends over many years. And from the photographs, you could see that even our family holidays become structural engineering field trips. So I'll start by saying a little bit about how I come to be here today, and then I'll move on to discuss the significance of cracking to the understanding of the behavior of reinforced concrete structures. Looking back, I can't believe that I've spent over 30 years of my life at Imperial College. It all started for me way back in 1986 when I enrolled on the Structural Steel Design MSc. Prior to that, I'd been working at Arup Associates, largely on the design of steel-framed commercial office buildings. Struggling with the complexities of lateral torsional buckling, I found myself spending more and more of my lunch times in the structural engineering section of Foyle's bookshop. My luck changed when, leafing through the Structural Engineer, I saw an advert for the Structural Steel Design MSc at Imperial College. I applied with some trepidation and was offered, to my surprise, both a place and also a bursary, which wasn't far off my salary in those days. I really enjoyed the MSc, which was a 9-month course in those days. At the end of the course, the then head of department, Professor Patrick Dowling, asked me whether I'd like to stay on for a PhD. After much thought, I declined and went back to Arup, where, to my consternation, having just spent a year studying steel structures, I was put to work designing reinforced concrete flat slabs, about which I knew nothing. Whilst checking some reinforcement on site, I was surprised to see that there was no reinforcement provided to connect the edge columns to the slab. This led me to have some fascinating conversations with Robin Whittle in Arup R&D. Robin introduced me to the complexities of punching shear design at edge columns, which is still a preoccupation of mine. This new interest in punching shear led me to visit the Polytechnic of Central London with Robin, and there we met with Professor Paul Regan, who was the UK's leading expert in punching shear. This experience whet my appetite for all things concrete. Subsequently, I left Arup and joined R.T. James, a small practice in Victoria. One day, seeking inspiration for a problem I was working on, I visited the library at the Institution of Structural Engineers. Coming out of the institution, who should I meet but Professor Dowling, who told me that he had a job coming up in the department as a lecturer in reinforced concrete design. Would I be interested in applying? I was, and to my great surprise, I was appointed. I arrived in mid-October and was giving my first lectures a few weeks later. Whilst in post, I studied for my PhD, which was on the topic of the design of beam column joints. As the Romans could have told you, concrete is strong in compression but weak in tension. One solution is to build domes, of which the Pantheon in Rome is a truly extraordinary example. The other solution is to reinforce the concrete with steel bars, as shown here. This is what we know as reinforced concrete. Having fixed the reinforcement, the next step is to place the concrete, as we see here, for a slab being cast with some rather stiff concrete in the structure's laboratory. Here we have some applications. So on the left, we have a concrete core that's been jump formed. The function of the core is to resist lateral loads on the building, and it also houses the stair and lifts. On the right, we have a flat slab building, and here, note the elongated or blade columns, which create interesting problems with punching shear design, as we will see later. Concrete structures are designed using design standards. Whilst fundamental behavior doesn't change with time, codes of practice are continually evolving. Over the course of my career, I've seen CP110 replaced by BS8110, BS8110 replaced by Eurocode 2, which itself is about to be reissued with substantial changes. Over the past decade, I've had the privilege of working on the development of the design rules for Shear in the next generation of Eurocode 2. The big change here is the replacement of the empirically based design equations in the current code with the mechanically based critical shear crack theory developed by Professor Mutoni and co-workers at EPFL. To explain the significance of cracking to an understanding of the behavior of reinforced concrete structures, I'm going to talk about two problems. The first relates to shear in short shear span beams, and the second to punching shear. Listed in the slide, you'll see the names of all the PhD students who have helped me in this endeavor. For the non-structural engineers amongst you, I will explain what I mean by shear. So the top figure shows a simply supported beam with a central point load. If I cut the beam to form a free body diagram as shown below, you see that I need to introduce a vertical shear force and bending moment to maintain equilibrium. Reinforced concrete members can fail in either shear or flexure. Here we have a reinforced concrete beam without shear reinforcement that's failed in shear. We increased the loading on the beam in increments of 10 kilonewtons, marking the cracks as we went. At a load of 120 kilonewtons, all the cracks were small. There was no signs of imminent failure. Yet, as we increased the load from 120 to 130 kilonewtons, the beam suddenly failed with a bang at 126 kilonewtons. This type of failure occurs without warning and should be avoided. Here we have a short shear span beam. The behavior of this is quite different. Once diagonal cracking has formed, the beam behaves like a tied arch, as shown, with the applied load being transferred directly back to the supports through the concrete acting in compression. Looking at the numbers on the beam, we see that the diagonal crack on the left-hand side had penetrated almost to the top of the beam at a load of 250 kilonewtons, yet the beam went on to carry a maximum load of 652 kilonewtons. Failure finally occurred as a result of the diagonal shear crack fully penetrating the flexural compression zone, separating the beam into two halves. So from tests like that, we draw the conclusion that the shear strength of reinforced beams without shear reinforcement depends on the ratio of the shear span to the effective depth. Here this is shown in the form of the Kearney Valley. On the vertical axis, I'm plotting the ratio of the bending moment at failure to the flexural capacity of the section corresponding to reinforcement yield. And on the horizontal axis, I'm plotting the ratio of the shear span to the effective depth. And we see that within region 1, where A upon D is greater than 6 to 7, the beam fails in flexure. In region 2, with A upon D between 2 and 6, the beam fails in shear at an almost constant shear force, depicted VC. For A upon D less than 2, the shear resistance is enhanced through arching action, as we saw in the previous slide. I will focus a little bit on shear enhancement in the next slides. As Aurelio will testify, the laboratory tests we tend to do tend to be quite academic. The loading arrangements which we examine are not always very representative of practice, where, like for this beam, we can have complex loading situations. So here the beam is loaded both within and outside 2D of the vertical column supports. this type of loading situation is not generally investigated in laboratory tests. Design methods for concrete structures can be classified as either empirical or mechanically based. So the slide here shows the design equation for the shear resistance of beams without shear reinforcement in the current Eurocode. This is an entirely empirical equation. Its range of applicability is limited to the range of the variables considered in its derivation. Mechanically based models are more versatile, as we'll see. We can use them to make predictions about situations we haven't examined experimentally. Both Eurocode 2 and the previous UK code, BS 8110, adopt empirical methods to account for shear enhancement through arching action. So here I'm showing a beam where the point loads are applied within 2D of the support. So the shear strength is enhanced above the basic shear resistance of VC. BS 8110 deals with this problem by enhancing the basic shear resistance VC by the multiple 2D divided by AV. This approach is adopted in the UK National Annex to Eurocode 2 for bridges. Eurocode 2 adopts the alternative approach of reducing the design shear force, P here, by the multiple AV divided by 2D. In this particular case, these two approaches lead to the same failure load. The situation becomes more interesting when we have a beam loaded with concentrated loads both within and outside 2D of the support. So according to BS 8110, we need to check two failure planes. So the first is between the support and the innermost point load, where the shear resistance is increased by this multiple 2D divided by AV. We also need to check for shear between the point loads where the shear resistance is equal to VC. So this results in this equation here for the failure load P. Using Eurocode 2, we calculate a reduced design shear force. So that's found by multiplying the load of a half P by AV divided by 2D, and then we add to that a contribution of a half P from the central point load, and we equate that reduced design shear force to VC. In the chart, I've plotted the failure loads corresponding to the shear enhancement methods given in BS 8110 and Eurocode 2. And what we see is that the BS 8110 method gives consistently higher shear resistances, raising the question of which of these methods is correct. This is a practically significant problem because this approach here is actually used in practice for the design of bridge structures to Eurocode 2. To investigate this problem, we tested a series of 4 beams without shear reinforcement. The beams were 4.35 meters long. Their cross-section was 500 millimeters deep by 250 millimeters wide. This slide shows the adopted loading arrangements, the maximum shear forces at failure, and also the crack patterns as determined by digital image correlation, and the widest cracks are shown with the red contours. So here at the top, we have the first beam loaded with a point load positioned at 1.5D from the support. The next beam down was loaded with a load of 0.4P at 1.5D and the load of 0.6P at 3D from the left-hand support. The loading arrangement of the third beam is statically equivalent to that of the second, with the load of 0.4P replaced by 2 loads of 0.2P positioned at 1.1D and 1.9D from the left-hand support. And then finally, the fourth beam was solely loaded at 3D, where we have no significant shear enhancement. Looking at the maximum shear forces at failure of these beams, we see that the beam just loaded at 1.5D was significantly stronger than the other beams, all of which failed at comparable maximum shear forces. This slide compares the measured shear resistances with those calculated using the design methods given in Eurocode 2 and the UK National Annex to Eurocode 2 Part 2, which uses the BS8110 method. What we see is that the BS8110 method overestimates the shear resistance of the beams simultaneously loaded within and outside 2D of the support. We also see that both methods significantly underestimate the shear resistance of the beam just loaded at 1.5D from the left-hand support. To investigate this problem more thoroughly, we looked at the shear transfer actions. So here we have a free body diagram created by the critical shear crack. So in the figure, I'm showing the various contributions to shear resistance that act along this critical shear crack. So at the top here, we've got a contribution from the uncracked flexural compression zone. And then at the top here, where the crack is very narrow, we have a contribution from the residual tensile stress in the cracked concrete. And then moving down the crack, we have a resistance from aggregate interlock. And then finally, a contribution to shear from the reinforcement bars themselves. And we refer to this as dowel action. You might be wondering how we can transfer shear through cracked concrete. The answer lies in the fact that the cracked surface is rough, as shown here. So consequently, there's a mechanical resistance to sliding. We can measure this resistance to shear through aggregate interlock in push-off tests, as shown here. And from tests like these, we can determine constitutive relationships relating the shear resistance to the crack opening and sliding displacements. We process the digital image correlation data from the tested beams to obtain the crack opening and sliding displacements as we increase the load on each beam to failure. These crack opening and sliding displacements are plotted along the crack as vectors in these figures. So making use of that crack opening and sliding information, we were able to calculate the contribution of each shear resisting mechanism as we increased the loads to failure. So the results are shown in these central charts, and what we see is that the relative contributions of each action vary both with loading as we increase the load to failure, but also vary with loading arrangement. Over on the far right, I'm showing the relative contributions of each mechanism at peak load. And we see that the behavior of the beam just loaded at 1.5D, which resisted by far the greater load, is quite different. So here the majority of the shear force is resisted by the uncracked flexural compression zone. Conversely, the beam just loaded at 3D resisted the majority of shear through aggregate interlock, as shown here. It is possible to develop design models to estimate the shear resistance of short shear span beams based on the crack kinematics. That's something we've looked at, but here I'm looking at the alternative approach of strut and tie models. So here we represent the force transfer through the beam using a series of struts and ties. And the figure shows that the geometry of the strut and tie model is dependent on the loading arrangement. In our model, we related the compressive strength of the struts to their angle of inclination and also the strain within the flexural reinforcement. So physically, relating the strut strength to the reinforcement strain is equivalent to relating the strut strength to the width of the critical shear crack, which is in turn related to the reinforcement strain or extension. As the critical shear crack widens, the contribution of all the shear resisting mechanisms reduces, leading to a reduction in the compressive strength of the strut. This chart compares the predictions of the strut and tie model with the measured strengths of the tested beams. And so that's the pink line here. And so you could see that the strut and tie model gives excellent predictions of the failure loads of the beams loaded at 1.5D and 3D, and also for the beam just loaded at 1.5D. For the beam loaded at 3D, the sectional model in Eurocode 2 we use to calculate VC gives the best predictions. We also see that the strut and tie model gives superior predictions to the purely empirical design methods adopted in BS 8110 and Eurocode 2. So in this case study, I hope that I've convinced you, first of all, that laboratory tests are important for establishing the behavior of reinforced concrete members, particularly in shear. Detailed measurements of crack kinematics give us interesting insights into shear resisting mechanisms. And then finally, and perhaps most importantly, hopefully I've shown you that mechanically based design models are preferable to purely empirical ones. Moving on, I'd like to look at the problem of punching shear. In the figure, I'm showing a flat slab building. These are very commonly used in the UK for residential construction. As shown in the figure, the flat slab consists of a solid slab supported by columns without any downstand beams. The key challenges in the design of a flat slab are firstly control of deflection and second, avoidance of punching shear failure. So this image here shows a slab that's failed in punching shear, and you can see that that's characterized by the formation of these diagonal shear cracks in the slab around the column. At failure, the slab separates from the column, leaving a cone of concrete behind attached to the column. Punching shear failure is undesirable since it can lead to a progressive collapse where the failing slab collapses onto the slab below, causing it to fail in turn. This is known as a pancake failure. Codified design formula for punching shear have traditionally been obtained from curve fitting the results of laboratory tests on isolated punching shear specimens. The isolated specimens are intended to replicate the zone of slab inside the line of zero radial bending moment. Over here we have a punching shear slab being tested in the structures laboratory. This slide shows typical reinforcement arrangement in a punching shear test. The shear reinforcement consists of double-headed shear studs which are arranged in a radial pattern as shown. In a punching shear test, the slab is typically supported at its center, either on a bearing plate or a column as shown here, and then we load the slab around its perimeter, typically with 8 equal point loads. Under load, radial and circumferential cracks develop as shown, and we increase the loads until punching failure occurs. The design method for punching shear in the current Eurocode is purely empirical. So to obtain the punching resistance, we multiply the cross-sectional area of the basic control perimeter, which is situated at twice the slab effective depth from the column face. We multiply that area by the design shear stress at failure. So that's a purely empirical equation, so it's not useful for making predictions about behavior for boundary conditions not considered in the experimental tests. In 2008, Professor Mutonyi wrote a seminal paper in which he developed the critical shear crack theory for punching failure in slabs. The theory relates the punching resistance to the slab rotation. The basic idea is that the opening of the critical shear crack reduces the strength of the diagonal strut carrying the load back to the column. So this concept is similar to that which we adopted in our strut and tie model in case study 1. So in its original form, the equation was semi-empirical, but more recently, Aurelio and his co-workers at EPFL have developed a refined version of the model which is based on the crack kinematics and the constitutive relationships for each shear resisting mechanism. The critical shear crack theory has several advantages over purely empirical design methods like the one in the current Eurocode. In particular, it allows the influence of differences in boundary conditions between isolated test specimens and continuous slabs to be investigated. And my research has focused very much on exploring the consequences of relating punching resistance to slab rotation. The issue which I'd like to consider is that of changes to codified design method for punching shear over the last 50 years. So over this time, we've seen CP110 replaced by BS8110, which in turn was replaced by Eurocode 2, which itself is about to be reissued with significant changes to the design rules for punching. Somewhat surprisingly, with each revision to the code, the amount of shear reinforcement required has increased significantly. This is due to both more test data becoming available and also changes in design philosophy. This naturally has implications for the assessment of older structures. So the problem is illustrated in this slide here, where I'm comparing the amount of shear reinforcement required by PS8110 1985, Eurocode 2 2004, and Model Code 2010. The large increase in required area shear reinforcement between BS8110 and Eurocode 2 is particularly striking. And this raises the question of whether slabs designed to BS8110 are safe. And bear in mind that there must be tens of thousands of slabs that have been designed to BS8110. We used the critical shear crack theory as implemented in Model Code 2010 Level of Approximation 4 to investigate this problem. The analysis accounted for the beneficial effect of slab continuity on punching resistance. This is something that is not normally considered in design. So in this exercise, we compared the resistances of an isolated specimen similar to the specimen we test in the laboratory with that of a continuous slab. We simulated the continuous slab by modeling 1/4 of a 7.5 meter square internal panel We calculated the rotations using nonlinear finite element analysis, and we simulated the slab continuity in two ways. So first of all, we applied rotational fixity to the edges of the 1/4 model, and then we also applied axial fixity in addition to the rotational restraint to simulate the effect of compressive membrane action. The results of this exercise are shown in this figure here. So on the vertical axis, I'm showing shear resistance and rotation along the horizontal axis. So plotted in the graph are resistance curves. So the resistance depends upon the amount of shear reinforcement provided and also the slab rotation. So as the rotation increases, the critical shear crack gets wider, and consequently there's a reduction in shear resistance. So that's reflected in these three curves here, which correspond to the shear resistances calculated with, first of all, the amount of reinforcement required by BS 8110, then the amount of shear reinforcement required by Eurocode 2, and then finally the amount of shear reinforcement required by Model Code 2010, which, remember, is based on the critical shear crack theory. Also shown in the figure are these load rotation curves. So the failure load is given by the intersection of the load rotation and the resistance rotation curves. So first of all, we have the green curve, which corresponds to the rotation of the isolated panel, similar to that which we test in a laboratory. And then these two curves here represent the response of the continuous slab. So the lower of the two curves is the slab just with rotational restraint at the edge. And then this one here is the slab with both rotational and in-plane restraint. Also shown on the curve is the design shear stress corresponding to the load that was used to design the flexural reinforcement for the slab. If we look at the results, we see that the failure load of the isolated test specimen is below the required design shear resistance. However, when we account for the beneficial effects of continuity, which has the effect of reducing the rotations and hence increasing punching resistance, when we account for that, we find that even the slabs with shear reinforcement designed to BS 8110 are safe. So clearly the slabs designed to Eurocode 2 and Model Code 2010 have a greater reserve of safety, but all three designs have adequate resistance to resist the design load. So to my mind, this raises interesting questions for code writers to consider. In the previous slide, you will have seen that finding the punching resistance using Model Code 2010 level of approximation 4 requires post-processing of data obtained using nonlinear finite element analysis. To automate this process, we developed a joint shell punching model. The model was developed by Andriy Setuan, who looked at internal columns, and then by Dima Abu Salma, who extended the model to look at edge and corner columns. So in the model, we modeled the slab with nonlinear shell elements. These elements are unable to model through thickness shear failure. So consequently, we introduced joint elements around the punching control perimeter at 0.5D from the column face. So the shear resistance of these joints is calculated using the critical shear crack theory. The key challenge here is that the shear resistance of the joints depends on the maximum rotation, which occurs near the line of radial contraflexure, rather than at the joints themselves. So to solve this problem, we made use of a rather clever joint formulation developed by Professor Izzadin. So the joint elements got 4 nodes, of which nodes 1 and 2 are structural, so they're placed on the control perimeter. Nodes 3 and 4 are non-structural, and they're made use of to calculate the relative slab column rotation. So node 3 is placed on the line of radial contraflexure, and node 4 on the column chord just above the slab. So we can calculate the rotation of each sector of the slab from the difference in rotation of nodes 3 and 4. And then finally, the model is also able to simulate the post-failure punching resistance, which is useful for assessing progressive collapse scenarios. A common design problem is that of assessing punching shear failure at elongated or blade columns. These are often used in residential apartments because they can easily be hidden in walls, unlike square columns with the same cross-sectional area. This slide shows that the through-thickness shear force tends to concentrate around the corners of large columns and elongated columns. So Model Code 2010 deals with this problem by neglecting the part of the control perimeter that's further than 1.5D from the column corners. To study this problem more fully, we carried out an investigation using 3D nonlinear finite element analysis with solid elements in Athena. This is the most accurate means of simulating punching failure, but it's not suitable for practical use due to its high computational cost. We calibrated the model using experimental data from the literature, and as shown here in this chart, we obtained good comparison between the calculated results and the experimental ones. To investigate the problem further, we looked at the distribution of through-thickness shear around the control perimeter. So the results are plotted here, and what we see is that the shear concentrates around the short side and the diagonal of the control perimeter. But as we move along the long side, we see that the shear force drops off significantly. Despite that, there's still a significant contribution of shear resisted along this part of the perimeter that is neglected by Model Code 2010. Having calibrated the model, we used it to carry out some parametric studies in which we looked at the effect of systematically increasing the long side of the column. So the results are shown here. And on the basis of that parametric study, we refined our joint shell punching model. And we did that by introducing one-way joints along part of the control perimeter that is neglected by Model Code 2010. Having developed this refined joint shell punching model, we made use of it to examine the problem of punching shear at the corner of shear walls in multi-story buildings. So this picture is showing on plan at 1/4 of the floor plate. And then this is the central core, similar to the one we saw at the beginning of the lecture, which is there to resist lateral loads. This slide illustrates the problem. It's showing the through-thickness shear force. We see that the shear force concentrates around the corner where there's a potential issue of punching failure. We modeled the transfer of load from the slab into the wall using the joint shell punching model. So around the corner of the wall, we positioned punching shear joints. Then we have a small gap, and then we introduce one-way linear joints which simulate one-way shear. Based on the studies we carried out using this model, we proposed a simplified method for checking punching shear at the corner of core walls like this. And recently, Dima Abu Salma has extended the joint shell model to investigate punching failure for complete floor plates, like the one shown here. So in this case study, I hope that I've convinced you of the advantages of using mechanically based design models. So the key point here is that with the mechanically based critical shear crack theory, we were able to show that slabs designed to BS8 110 with less shear reinforcement than would now be required are often safe. And the reason for that is that the shear resistance is increased through the benefit of having slab continuity and compressive membrane action. Simple empirical design equations like that given in the current Eurocode are unable to solve complex problems of that type. A few thoughts for the future. So first, reusing rather than building new structures will increasingly become the bread and butter of structural engineers. This presents many challenges, the first of which is assessment of structures designed to older codes using current design guidance. So an example of this is the slab we looked at where the shear reinforcement was designed to BS8 110. Another challenge is in the assessment of structures with non-code compliant reinforcement detailing. But perhaps the holy grail is to be able to estimate the proximity of failure from the crack pattern alone. So I have a couple of slides to illustrate this. So here we have a beam that's been loaded to failure in shear. At this point, the load was 1,300 kilonewtons. Looking at the beam, it's clearly cracked, but it's not at all obvious that it is about to fail. We increased the load to 1,396 kilonewtons, big bang, and catastrophic failure. So the challenge is how, from the crack pattern alone, can we ensure the safety of our structures? So that brings me to the end. Thank you very much for listening, and I think we have some time for questions.
Thanks very much. So it's all in the cracks. Now I understand it, because it's linked to the possibility of being able to predict failure. I understand. We have time for one or two questions. We do have some roving microphones, please. And when we get to you, if you don't mind, please state your name and affiliation, and then ask the question. So we'll do it alternatingly with those colleagues online. So let's start with a question from the room, please. Yes, Stephen. The microphone coming.
Thanks, Robert, for a great talk. It's really great to hear about what others are doing in other sections in the department. I'm Stephen Smith and Head of Environmental and Water Resource Engineering, so slightly different area. But Robert, you're sort of talking about cracks. I was just wondering whether the composition of the concrete made any difference. You know, if you're using different types of cements or different aggregates or different sort of formulations, does that affect the performance of cracking?
That's a very good question, Stephen. Yeah, the answer is yes. So there are two aspects to it, I think. So first, the load at which the concrete cracks is obviously dependent on the concrete tensile strength, which depends on the mix design. The shear transfer through cracks depends upon the crack roughness, which depends upon the size of the aggregate, and also on whether or not the cracks pass around or through the aggregate. And then the other project, which I have going on at the moment, which I didn't talk about, relates to restraint-induced cracking. And there, whether or not cracking occurs is very much dependent on the mix of the concrete. So, for example, using GGBS, you can reduce the heat of hydration, which reduces the risk of cracking. Also, the cracking depends on the amount of shrinkage of the mix. So, yes, excellent question.
A question online, please, Karim?
Yes, there's a question from Toko asking, what is the influence of support elongation on punching resistance at internal slab column connections without shear reinforcement?
Yeah, so the key thing is that the shear force concentrates around the ends of the column. So essentially, as you increase the length of the column, you get less benefit in terms of increased shear resistance than you might expect.
Thank you. One more question from the audience, please, in the room. Yes, a question here, please. It's coming. Don't worry, there's a microphone just coming.
Adamandia Campbell, ex-alumnus. I wondered what the impact of time was. So if we're looking at buildings that are 50, 60, 100 years old, do we expect time to cause a critical failure, in effect, and should we be prepared for that?
That's a very good question as well. so yes, there are obviously several aspects to it, aren't there? So there are changes to design rules, as we saw sort of recent design rules for punching shear are more onerous than ones in the past. But you're right, there is also deterioration of structures with time. So with older structures, you have the combination of those problems of reduced strength due to deterioration, but also the design quite possibly not in line with current guidance.
Online? Question?
Question from Lynn Simpson. I'm a specialist in finite element analysis working for Ramble, currently modeling nonlinear concrete shear in Diana. Could you repeat the name of the software you used? Thank you.
Yes, it's Athena.
That was an easy one. There was one from the gentleman at the back. Last one, please. Thank you.
Hello, my name is Sanusi. I'm an MSc Structural Engineering. So my question is, you talked about the increase of reinforcement as the code progresses, that is for shear. So my question is, does that make concrete structures more unsustainable now because of the increase in reinforcement? Thank you.
That's a very interesting question. I think you probably need to think about sort of how versatile the structure is in terms of reuse. So I think there's more to sustainability than just minimum use of materials. But yeah, no, a very interesting question there.
Okay, thank you very much. In the interest of time, I think it's wonderful to see how much, Robert, you're contributing to this most safety-critical work. So I feel a lot safer now. Thank you very much. And it's now my pleasure to invite Professor Aurelio Muttoni to give a vote of thanks. Professor.
So, ladies and gentlemen, dear colleagues, good evening. My name is Aurelio Muttoni. I am a part-time full professor at the Swiss Federal Institute of Technology in Lausanne, and also a structural engineer in a firm that I have founded some years ago, active as structural engineer. So I hope that you will understand my continental English with a little bit Italian, French, and German accent. So, I know personally Professor Vollum since many years, in fact, when we met in symposia and other similar events organized by the International Federation of Structural Concrete. This is the English wording of Fédération Internationale du Béton. Since 2012, I had the pleasure of working with Robert on several open questions related to the behavior and to the design of concrete structures in the frame of the works of the European expert group dealing with the draft of the second generation of the European Standard for Structural Concrete. So you have already heard about this very important work. This is really a very important work with a potentially tremendous impact on practice, since we estimated about 500,000 structural engineers in Europe, including UK and also my country, will use this standard to analyze, to design, and to assess concrete structures. So you can imagine that the impact that it can be quite significant. In all these activities, I always had the impression that we share several interests and that we have a very similar approach in our researches. This was very interesting. And it's only when I read your biography, Robert, that I understood the reasons, in fact. We both came back to academia after spending about 1 decade in practice, full-time in practice. And with this respect, unfortunately, combining practical experience with solid theoretical knowledge is more and more rare in many universities. Nowadays, unfortunately, it is quite uncommon that colleagues can return to research and start an academic career after spending several years in practice. I think that colleagues in academia know the reasons. The result of this is that too many investigations nowadays are conducted on topics which are not relevant neither for current nor for future practice. And this is really a pity, in my opinion. The research by Professor Vollum is not only mostly practically oriented, but it is also very rigorous and theoretically sound. You heard about the mechanically based models. To me, this is a key issue to avoid empirical research and to go much more in a theoretical research. His publications reflect this approach. They are always at very high level. And here you see, for instance, the paper award by the Magazine of Concrete Research journal, and his PhD students have been awarded in the PhD symposia by FIB. Our topics of interest also are similar, and this is not surprising for the reason that I have just mentioned. For instance, you have already heard, we have worked both, and we still work on shear in concrete members. With this respect, I remember that late Professor Paul Regan, who was well known for being able to combine research, excellent research, and practice, wrote a very nice paper about 30 years ago. The title of this paper was Research on Shear, a benefit to humanity or a waste of time? It was an excellent paper. Of course, despite the provocative and funny title, he was trying to convince the readers that research on shear is something very useful. But I'm not sure that he has been very convincing on it. At that time, many colleagues argued that research on shear led to too complicated code formulae with limited benefit in terms of economic advantages for design. I remember then when I decided to return to academia, I submitted my first research proposal on punching of flat slabs. At the end, I got the research, despite the research grant, despite the fact that I received several negative comments by the reviewers. Most of them argued that after so many years of research, there was nothing new to investigate, and that punching shear was not a hot topic anymore. This was 20 years ago, more than 20 years ago. In fact, my interest was mainly due to the fact that at the end of the 90s, in our engineering office, we already started assessing existing structures, and in many cases, the safety level, according to the standards of that time, was insufficient, and this was always a big problem, in fact. In addition, I had the impression that some practical situations were not addressed correctly in the standards of that time. The experience has shown that my intuition was not so wrong, and in the following years, I had unfortunately to work on as an expert for several accidents, in fact, related to punching. And the assessment of existing structures became more and more important. Nowadays, there are many colleagues working in this field, and there is a large amount of papers published every year on punching. Not all of them with new, relevant ideas, unfortunately. Dear Robert, I am very happy to see that there are still colleagues who decide to conduct experimental and rigorous theoretical research on topics which are significantly related to practical and industrial issues, focusing in improving the efficiency of structures, in simplifying the construction process, and allowing to develop more efficient design methods. Nowadays, we have an additional tremendous challenge, in my opinion. Our structures should become more sustainable. I am very much convinced that there is a need for new solutions, new developments, using sound theoretical approaches, and perhaps producing a real benefit to humanity. Thank you very much.
Thank you very much, Professor Muttoni. So mine is just to say a humongous thank you for attending today on behalf of the department and the university, and to invite you, please, to join us for a drinks reception just outside, get to know each other, network, and so on. And when you're done, please have a very safe journey back home. So thank you very much for coming. Thank you.